through projects. In this video, we are going to explain about the project title Coffee Fruit Recognition Using Transfer Learning. Introduction. The project focuses on developing a robust system using transfer learning techniques, which involves leveraging knowledge from one task to improve performance on a related task. This approach enhances the accuracy and efficiency of coffee fruit recognition. Addressing the critical need for accurate and efficient identification of coffee fruits is vital in various stages of coffee production, including harvesting and quality control. By automating this process, the project contributes to streamlining production workflows and ensuring consistent quality. Traditional methods reliant on manual inspection are prone to errors, time consuming, and subject to human subjectivity. Automated methods face challenges such as lighting variations, occultations, and diverse backgrounds, resulting in suboptimal performance. By adopting transfer learning techniques, the project aims to overcome these limitations. Leveraging transfer learning involves fine tuning a model trained on different tasks to perform coffee fruit recognition effectively. This approach capitalizes on pre existing knowledge learned from large data sets, reducing the need for extensive label data and enhancing the model's performance. The project utilizes advanced deep learning architectures to handle the intricate patterns and variations present in coffee fruit images. These architectures are specifically designed to extract meaningful features from complex data set, further improving the accuracy and robustness of the recognition system. Objective. The project's main objective is to develop a robust system for accurately identifying coffee fruits through the utilization of transfer learning techniques, aiming to overcome limitations of traditional methods and enhance accuracy and efficiency in recognition. Employing a variety of algorithms, including MobileNet and Exception, which leverage transfer learning from ImageNet, alongside machine learning and deep learning techniques, the project seeks to achieve precise identification of coffee fruits, blending the strengths of different approaches. With a focus on predicting the ripeness levels of coffee fruits, categorizing them as half ripe, unripe, and ripe, the project aims to enhance quality control during production, ensuring consistent and reliable sorting processes. By improving productivity, quality control, and consistency throughout the coffee industry, the project's outcomes benefit stakeholders across the supply chain, encompassing farmers, producers, processors, and ultimately consumers, fostering positive impacts throughout the industry. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, databases SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing libraries. In this module, the necessary libraries and dependencies are imported into the project. This includes frameworks like TensorFlow and Keras for deep learning, Scikit-learn for machine learning, Flask for web development, and SQLite for database management. These libraries provide the tools and functionalities required for subsequent tasks in the project. Importing dataset. Here, the dataset containing images of coffee fruits is imported into the project. The dataset serves as the foundation for training and testing the coffee fruit recognition model. It consists of labeled images where each image is associated with the class label indicating the type or ripeness level of the coffee fruit. Data pre-processing. This module focuses on preparing the dataset for model training. Pre-processing tasks include resizing images to a uniform size, normalizing pixel values to a common scale, and augmenting the data to increase its diversity and improve model generalization. Data pre-processing helps ensure that the input data is in a suitable format for training the model. Data visualization. Data visualization techniques are applied to gain insights into the dataset. Common visualization methods include histograms to visualize the distribution of class labels, scatter plots for feature analysis, and image plotting to visualize sample images from the dataset. Data visualization aids in understanding the characteristics of the dataset and identifying any patterns or trends that inform model development. Splitting the data into train and test. In this module, the dataset is divided into training and testing sets. The training set is used to train the coffee fruit recognition model, while the testing set is reserved for evaluating the model's performance on unseen data. Training and building the model. This module involves training the coffee fruit recognition model using transfer learning techniques. Pre-trained deep learning models like MobileNet and Exception, which have been pre-trained on large-scale datasets like ImageNet, are fine-tuned on the coffee fruit dataset to learn to recognize coffee fruits accurately. The model is trained using the training data and adjusted to minimize prediction errors. Performance comparison. The performance of the trained model is evaluated and compared against baseline models or other algorithms using performance metrics such as accuracy, precision, recall, and F-win score. This module helps assess the effectiveness of the model in accurately identifying coffee fruits and provides insights into its strengths and weaknesses. Flask framework with SQLite for sign up and sign in. This module integrates the Flask web framework with the SQLite database to implement user authentication functionalities like sign up and sign in. Users can register for an account, log in securely, and access the coffee fruit recognition system. User authentication helps ensure secure access to the system and protects user data. User gives input. In this module, users interact with the system by providing input through the web interface. This involves uploading images of coffee fruits using a file upload feature or entering input data through a form on the web application. The given input is pre-processed for prediction. The input provided by the user is pre-processed to prepare it for prediction by the trained model. This involves tasks like resizing images to the input size expected by the model, normalizing pixel values, and extracting relevant features from the input data. Trained model is used for prediction. The pre-processed input data is fed into the trained coffee fruit recognition model, which predicts the class label or ripeness levels of the coffee fruit. The model applies its learned knowledge to make predictions based on the input data provided by the user. Final outcome is displayed through front end. The predicted outcomes, such as the classification result or ripeness level of the coffee fruits, are displayed to the user through the front end of the web application. This provides a user-friendly interface for interacting with the system and visualizing the results of the coffee fruit recognition process. Algorithms used to implement this project, we have designed the following algorithms. The first algorithm is MobileNet. MobileNet is a lightweight deep learning architecture designed for mobile and embedded devices. It consists of depth-wise separable convolutions, making it computationally efficient while maintaining good accuracy. In the project, MobileNet is used as a pre-trained model for transfer learning from ImageNet. It is fine-tuned on the coffee fruit dataset to recognize coffee fruits accurately. Coming to the next algorithm, which is CNN, Convolutional Neural Network. CNN is a class of deep neural networks commonly used for image recognition tasks. It consists of multiple layers, including convolutional layers, pooling layers, and fully connected layers. In the project, CNNs are employed for their ability to automatically learn features from images, contributing to the recognition of coffee fruits. Exception. Exception is an extension of the inception architecture known for its depth-wise separable convolutions. It aims to capture more fine-grained features by increasing the depth of the network. Similar to MobileNet, exception is used as a pre-trained model for transfer learning from ImageNet in the project. It undergoes fine-tuning on the coffee fruit dataset for accurate recognition. KNN, K nearest neighbor. KNN is a simple and effective machine learning algorithm used for classification tasks. It operates by assigning a class label to an input based on the majority class of its k nearest neighbors in the feature space. In the project, KNN is used as a traditional machine learning algorithm for coffee fruit recognition, particularly for its simplicity and ease of implementation. Coming to the next algorithm, which is support vector machine. SVM is a powerful supervised machine learning algorithm used for both classification and regression tasks. It works by finding the optimal hyperplane that separates different classes in the feature space, maximizing the margin between classes. In the project, SVM is employed as a traditional machine learning algorithm for coffee fruit recognition, particularly for its ability to handle high dimensional data effectively. Decision tree. Decision tree is a popular machine learning algorithm used for classification and regression tasks. It operates by recursively partitioning the feature space into regions based on feature values, ultimately leading to a decision on the predicted class label. In the project, a decision tree is utilized for their simplicity and interpretability, particularly for understanding which features are most important for coffee fruit recognition. Coming to the next algorithm, which is random forest. Random forest is an ensemble learning technique that combines multiple decision trees to improve classification accuracy and robustness. It works by training multiple decision trees on random subsets of the data and averaging the predictions to make a final decision. In the project, random forest is used as an ensemble learning approach for coffee fruit recognition, particularly for its ability to handle complex data sets and mitigate overfitting. Comparison graphs offer a visual breakdown of how our models perform across essential evaluation metrics. Models are compared with the evaluation metrics accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis we have algorithm name, and on the y-axis we have accuracy score. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is recall comparison graph. Here on the x-axis we have algorithm name, and on the y-axis we have recall score. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is precision comparison graph. Here on the x-axis we have algorithm name, and on the y-axis we have precision score. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is F1 comparison graph. Here on the x-axis we have algorithm name, and on the y-axis we have F1 score. F1 score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm which is performing best in all the evaluation metrics will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here I am copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are new users, we need to register first, but I have already registered myself. So click on login link here. Here we need to enter the username and the password which we have registered, and then click on login. We have logged in successfully and we are redirected to the production page. Here we need to upload the coffee fruit images, and after uploading the images, the application will predict the ripeness level of the coffee fruit. Now click on choose file to select the images. So here I am uploading the first image. Now click on open. So here we can see that the image is uploaded. Now click on upload button. So here we can see this is the uploaded image, and for the given input image, the type is unripe detected. It means that the coffee fruit is not ripe. Let us upload some more images. Click on try again. Now click on choose file. I'm selecting the second image. Click on upload button. So here this is the uploaded image, and for the given input image, the type is half ripe detected. So it means that the coffee fruit is half ripe. Let us upload one more image. I'm selecting the third image. Click on upload button. So this is the uploaded image, and for the given input image, the type is ripe detected. In this way, just by uploading the coffee fruit images, we will predict the ripeness level of the coffee fruit, whether it is ripe, unripe, or half ripe. Now click on sign out link here. The conclusion of the project is the project achieved its main goal by creating a reliable system capable of accurately identifying coffee fruits. It addressed drawbacks associated with conventional methods, paving the way for enhanced efficiency and precision in fruit recognition tasks. Utilizing transfer learning with deep learning models like MobileNet and Exception led to notable advancements in coffee fruit recognition. Leveraging pre-trained models enabled the system to attain higher accuracy and robustness in identifying coffee fruits compared to traditional approaches. The project's future trajectory involves refining the architecture of the developed model to optimize its performance further. Additionally, the exploration of additional data sets and the extension of the framework to other crops or industries are envisioned, highlighting the potential for broader applications and continued technological innovation. By integrating transfer learning techniques and combining deep learning with traditional machine learning algorithms, the project contributes significantly to the progression of automated recognition technology, especially in agricultural domains. This approach facilitates more efficient and accurate recognition processes with implications for various industries beyond agriculture.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.